All right, so let's look at 2-1 functions and their graphs. All right, so we're going to recall the following definitions. So first, write down what a function is. And again, if you need more time, you'll just pause the video. For every input, there is exactly one output. A domain is the set of input values. The first number of an ordered pair is the x value. So if you think of an ordered pair x comma y, this is the domain. And then the range is the output values, the y. So the y part is the range. All right, so make sure that we know those. Again, if you need to stop the video to write those down, please do so. All right, so let's look at another term. This is a relation. You don't need to write this one down. A relation is a mapping or pairing of input values with output values, such as an ordered pair. That's one way to write a relation. Another way is like using a table or an actual mapping drawing. Right? Some relations are functions and some are not functions. Again, you don't need to write that down. Just know that some relations are functions and some are not functions, but all functions are not relations. I know, that's exciting. All right, so decide whether the relation is a function. If so, we're going to give the domain and range. So let's look at the whole problem here. So we're looking at this. So remember that for each input, you can only have one output. So 1 maps to 2, 2 maps to 4, 3 maps to 4, and 4 maps to 5. So each of these numbers do not repeat. Each of the input values do not repeat. So the answer is yes. This is a function. So the domain are the input values, and use this set notation. So it's 1, 2, 3, 4, right? Because those are the input values. 1, 2, 3, 4. The output values are the range, and that's 2, 4, 5. Even though 2 maps to 4 and 3 maps to 4, you don't have to write 4 twice. So it's 2, 4, 5. All right, and then now we have the other stuff in our way. But look, we were right. Yay us. All right, next, we're going to decide whether the relation is a function. If so, we're going to give the domain and range. So 1 maps to 5, but then again here we see that 1 also maps to 7. Once 1 maps to 5, he's done. He can't also map to 7. So the answer is no, right? Because 1 maps to 5 and 1 maps to 7. You can't do that. That's wrong. And then we have this cute little thing here that tells us. So again, you can see it underneath the writing. All right, the next one is we're going to graph a relation, and we're going to need some graph paper. Luckily, I have some on the next slide. So we're going to write the relation as a set of ordered pairs. So do you see that 3 maps to -1? -1 maps to 1. On this one, 1 maps to 1, and 1 maps to 3. So hopefully you're like, oh look, that's not a function. And then 2 maps to -1. All right, now we're winners. Now we're going to graph the points. So if you want, you can just draw a coordinate plane. So here's a coordinate plane. You can draw one on your paper. And we're just going to plot those points. So I'm going to go over -3, down 1. Remember, you go over x and up and down y. Then I'm going to go over -1, up 1. You go over +1, up 1. Going to go over 1, up 3. And over 2 and down -1. So I graphed all 1, 2, 3, 4, 5 points. All right? And do you see that these two are on the same line? That's one way to tell when the same vertical line. That's one way to tell when something's not a function. Because one is mapping to 1 and 1 is mapping to 3. Whenever this number in the domain repeats, it has to have the same number it had the first time. So this guy here broke it. He's bad. All right, so write the relation as a set of ordered pairs. So again, hopefully you're able to do this. You might want to stop the video and make sure that you can do it. And if you did it right, here's the answers, and then we'll graph the points again. All right, so So -3, 1. So -3, +1, 2, +3, and 3, -2. Right? Yay, us. All right, so now we're going to look at the vertical line test, which is kind of what I was talking about before. So on a graph, on graph number 1, the one that I was showing about where I circled the points, draw several vertical lines that go through the points. So does one line touch more than one point? So if you remember on the example I did before, I circled the 2 points and the answer was yes, which means it fails the vertical line test. Anything that fails the vertical line test is not a function. It's a relation, but it's not a function. All right, so on graph 2, the second graph that we did, draw several vertical lines that go through the points. So this one, does one line touch more than one point? On that one, we had 3 different points in 3 different places. So if I draw vertical lines through them, does it touch more than one point? The answer is no. Right? Therefore, it passes the test. Therefore, it is a function. Right? A relation is a function if and only if no vertical line intersects the graph of the relation at more than one point. So write this down. So here's an example, and again, I would suggest that you draw this on your paper, just kind of sketch it on there, and see that this is not a function. Here's the vertical line, and you can see that the vertical line passes through this function in 2 places at the same x, which means x here maps to this y and x maps to this y. Right? So it's not a function. It fails the vertical line test. This one is a function. So if I draw, really it's kind of like an infinite number of vertical lines through this. Every single one of these vertical lines will only pass through this function one time. So yes, this is a function. And again, you might want to draw that in. I erased it so that you could see what the graph looked like. And here's this one, right? Picture yourself drawing 50 million vertical lines. So if we just draw all these vertical lines, we can see that no matter where we put the vertical line, it's only going to pass through the function in one place each time. And here's another one. All lines are all lines are functions except for one, and the one line that's not a function is the vertical line, x equals 2. All right, and here's another one. This is what an absolute value function looks like, and this one is a function. It passes the vertical line test. So I would suggest that you draw an example of each of these in your notes so that you have a good idea of what's going on. Oh, one more. See all those vertical lines? Yes, we're a winner. Okay, so not a function. We looked at this one before. Why is this not a function? Because a vertical line passes through it in more than one point, more than one places. This function here, this graph is not a function either, because if I draw these vertical lines, right, it fails here, it fails here, it fails here, right? Each of these vertical lines passes through the graph in more than one point, so not a function. This one is not a function because here's an example of a vertical line. It also fails here, it fails here, it fails here, it fails here. It only needs to fail one time. Like over here, it passes. Well, that doesn't matter because it failed at all these other places. So again, I would suggest drawing those in your notes so that you have an idea of what's not a function. All right, so here's a little example. Which graph is a function? So I didn't put the other graphs on there. I'm not sure what I was doing. But this guy here is a function, right? Here's the line. And no matter where we draw this through, it's going to pass in every place. All right, many functions can be represented by an equation in 2 variables. This should look pretty familiar, right? We've seen this in Algebra 2. We've even seen that a little bit in geometry. That's slope-intercept form. Right? So the question is, solution to these equations is an ordered pair, right? So remember that there's an infinite number of points that are true for this equation. And one example is the point 2, -3, right? So 2 maps to 3, which means that if I put a 2 in here for x, the input, the output would be a 3, right? So this is 2 times 2, which is 4. 4 minus 7, or sorry, a negative 3, because that's what that says. So when I put x in, I get negative 3 out, and that's what a function is. All right, and then there's also independent versus dependent. Independent variables are input, right? Typically the x. An example here is y equals 2x minus 7. X is independent. We can pick whatever x we want to put into this equation, but y is dependent upon what x we choose. Like if I choose x to be 1, well then y has to be negative 5. It doesn't have a choice. And if I want x to be 0, then y has to be negative 7. So y is dependent on x, but I can pick whatever I want for x. Right? And then dependent is just what we were talking about. It's the output variable. It's the y. It's the guy that doesn't get to have a choice. Okay? So now, here's the collection of all of coordinates that lie on this line here that I'm outlining, kind of. So when x, my input is negative 1, my output is negative 9. When my input is 0, my output is negative 7. You can see where those points would fall on the graph. When my input is 1, my output is negative 5. All right, so now looking at this one, we're going to construct a table of values, which is what we just saw. Right? We usually refer to these as T-chart. So if I say a T-chart or a table of values, you know what I'm talking about. Step 2, you're going to graph enough solutions, graph enough order pairs to recognize a pattern. So again, you want to write these steps down, and if you need more time, you're just going to pause the video. Step 3 is to connect the points. It may be a line or it may be nonlinear. Nonlinear like a curve. All right, so let's do an example here. We're going to construct or graph this line, and we know it's a line because the degree of x is 1, and whenever that's true, it graphs a line. We're going to use a table of values or a T-chart. So whenever you have a linear equation, you're going to use -2, -1, 0, 1, and 2 for the x's. And then the y's are going to be dependent upon what you get. So you're going to take each value of x and plug it into the equation. So this would be -2 plus 1, which equals -1. -1 plus 1 equals 0. 0 plus 1 equals 1. 1 plus 1 equals 2. 2 plus 1 equals 3. Right, so now that we have our table completed, we're going to graph the points. So -2, -1, -1, 0, 0, 1, 1, 2, 2, 3. And look, you see that all of our points are in a line. So we're going to go ahead and connect the dots, and because this is a line, we're going to put arrows on both ends. That represents that it continues forever in those two directions. And what we just did is we graphed using a T-chart. All right, so now let's look at function notation. This is f of x. So this is used for function notation. We'll see this throughout the year, f of x. All right, so when the x has a number, this is now f of 2. All right, so you can use function notation for a linear function such as y equals f of x. So, or sorry, y equals x plus 1. The y and the f of x mean the exact same thing. They're interchangeable. So this also could say f of x equals x plus 1 because y and f of x are exactly the same thing. They mean the same thing. Right? Yay, look at me. Notice that it's just another name for y. Magic. All right, sometimes we have g of x and h of x because we're cool. All right, so now let's look at some linear functions. I know, it's exciting. So guess what this is? Slope-intercept form. That guy's our friend. This is the linear function. Look, f of x instead of y. Awesome. So now we're going to do a little Shakespeare. To be linear or not to be? Let's see. Decide whether this function is linear. Is this function linear? Well, all you do is you look at the degree of the equation. That's a 2. Is a 2 the same thing as 1? No. So this is nonlinear. Anything that's even either makes an upside down U or right side up U or an upside down U. Then you look right here. Well, if it's negative, it's upside down. No, look, sad face. Can't quite see him because I colored all over him. This guy. So you look at the exponent on x, right? If there's no exponent, then a 1 is implied. Is this guy linear? Yes. Why? Because he has a degree of 1. Yay! Happy face. All right, now we look at this guy. Is this guy linear? Well, he has a degree of 1. However, these cute little bars are called absolute value, and absolute values look like this. Well, like a V, not with a little line in there, not a little curve. So it looks like this because the absolute value makes it positive, the distance from 0, and you can't have a negative distance from 0, so that brings the back side of the line straight back up. So, see this? No. Alright, so now we're going to evaluate a function. So, let's say we have f of lion, which is equal to 2x squared minus 3x plus 7. I promise I'm going somewhere with this. What you do is you just take whatever's in this little parentheses and you substitute it where every single time there's an x. So see, f of lion equals 2 times lion squared minus 3 times lion plus 7. We can do the same thing with little alien head. So I'm going to put an alien head here, and I'm going to put an alien head here. So watch. Magic. So that's all you do. Wherever's in the parentheses, you just put it where the variable is. So let's do that for math this time. So here's the problem, right? F of negative 2 equals negative x squared minus 3x plus 5. Notice that the negative stayed in the same place. Where the x was, we put a negative 2. There was a squared. This guy has a squared. We bring the negative down. We have the 3 down, and then instead of putting an x, we put negative 2, and then we bring the plus 5 down, or plus, and the 5 down. So the only thing that changes is where the x's were. And then you just solve it. So this is negative. Negative 2 squared is positive 4, so the negative is out front. Plus, negative 3 times negative 2 is positive 6, plus 5. Order of operations, add and subtract from left to right. So 2 plus 5 equals 7. And now we're winners. So now we're going to evaluate the function for the given value of the variable. So on this one, what are we going to do? Well, look, it's function notation, which means plug this guy in where the x is. So here's the solution. Look what I did. I put negative 2 there, and I put negative 2 there. So the 2 stayed the same, the minus stayed the same, the 3 stayed the same. The only thing that changed was the x. Notice the x went away and the negative 2 came in its place. And then you just simplify. That's negative 4 minus 3, which makes negative 7. Now we're winners. All right, that's that. So if you have any questions, come see me tomorrow. Otherwise, we'll be practicing tomorrow in class so that we can be winners.